You got plenty of lines in the middle. So how do you know which line is the best line to split? You get the test case, they're not necessarily exactly separate like this. They might have a test case here, a test case here. Are you going to be still good? That's the question. You know, you did the perfect fine for the training case. You can overfit. That's always you can get 100. If you use decision tree, go to the last of the problem, you can always get 100% in the training. But that does not mean anything to the test case because the overfitting, right? So now the question is pretty simple. Which line is the best? Intuitively, which one you think is better? This line or that line? Tell me.
45 degree.
Yeah, this one looks better, right? Not because it's a 45 degree. Intuitively, you can say these two are too close. Can you see? This too close means you could be overfitting a little bit of noise. This guy could cross this line, right? A little bit of deviation. This guy could cross this line. Are you with me? But here, you look at the distance. The closest one are these two, right? Can you see? It bisected this two closest point. Can you see? Okay, those 2 points later on you're going to recognize. It's called support point. So that's what happened. You get these two parallel lines give you the maximum margin. The big buffer zone you have, you call it margin, the better off you're going to sustain for the noise, right? Are you with me? When you test the case coming, see, this buffer zone is so long, if you anything somewhere here, you still can separate it, right? So you got these two support line and this line cut in the middle, that mathematically approved is the best solution. Give you the maximum margin. See, so far, I just give you the intuitive idea, not involved in the math. This is the qualitative model, we'll say conceptual model. And the next, we want to look about the math, how we write down all those things, and use the computation to figure it out. That's the next question. So now you know how to do this question, right? For the two type of midgets. And you just need to cut these two lines, which is the closest one, and then you cut in the middle line, kind of related with a regression rule. So what you have, do you know the dot product plus a constant? Let me get you a little bit of a review about the calculus 3. And if the question left over is how do you figure this margin? That's what I saw talking a moment ago. When I put one line, because you only have 2D, it's easy to demonstrate. But if I have 3D, you need to change these two lines into two planes, right? If I have 12D, then you call it superplane, the same idea, but you need to get the distance between them, okay? It's just dimensions more. But the same idea, you need to get this marginal. And now, the margin is this. Look, this is +1, and you see 1 equals this equal -1, this equal +1. This dot product is this W. Look, this W is the weight. This W is the n I talked a moment ago, right? It's the normal vector, right? To the superplane. And this x is the x, y, z. I talked a moment ago. X is x1, x2, x3, all the way to xd. Depends on how many dimensions you have. But this dot product, the equal sum constant, is really a plane. But we call it superplane. We do not know how many dimensions it has. 3D, I showed you. 2D, you look at here. But if it's 12D, same idea, same idea. The key is you understand how this comes from. This is what I showed you a moment ago. See, 1, -1, when you subtract these two planes, the b cancels out, and the 1 minus -1 is 2, right? Are you with me? And then on the bottom, that's the normal. The norm is a square root. It's just like the Euclidean distance, the square root of W1 square, W2 square, put all the weight square. So now, if you are with me, what's the question now? To maximize this margin means you need to maximize this, right? Right? That's it. Now, that's how you do the mathematics modeling. You start from some common idea you agreed, then you write it into math. I need to maximize that. Under what condition? Those need to be somehow positive. See? By the design, you cannot have the win antenna that are negative. In application, most of them are positive, right? The weight could be negative. So, I don't like things on the denominator. To maximize this is the same as minimize this. Can you see it? You square it. It's a distance, right? Yeah. You want to minimize, you can maximize that. That's the W squared. And then the constraint, what that mean? Just that means one in this side, another on this side, right? And that is the buffer zone. You want to maximize the buffer zone and then make it maximize separate, right? So you want to minimize this, just turn the things around and make it mathematically easier. Under this condition. This condition means yi, we have two classes, positive and negative. The y either equal positive 1 or negative 1. This is the binary class. Times this. Either bigger than 1, or if this is negative 1, really is less than negative 1, right? If this is negative 1, you remember the equation, right? So if yi is positive on this side, if yi is negative, means in this side, on this side. Because negative, you need to change the direction of the equality, right? Okay, that's the standard optimization problem. We call it a mathematics programming, or sometimes call it quadratic programming. Why quadratic? That's a square. That basically is W1 square plus W2 square plus W3 square, in the same way like my 3 square plus 4 square plus 12 square, right? That's the same thing. This is the math built by Lagrange hundreds of years ago as Euler's successor, you know, in hundreds of years ago. But without the computer power, it's very difficult to do in those days. The basic idea of the algorithm is pretty simple. You put this, we call it, anybody know a little bit of a simplex method? Like a polygon, a convex gun. Now, this is the idea. Let me just draw it. You really look for the shortest 2 points. Now, this point you need to touch this line, this point you need to touch that line. That's why you take the corner point. And the equality hold at these 2 points. That's when you usually, intuitively, you're going to get your maximum. And then you're going to draw this, because these are the 2 lines, and then you get the bisector plane here. That's pretty much simple idea if you only get 2 lines. How do you get this down? The Lagrange method, basically, you need to change the equation into equation. The maximum usually happens in some corner point. And then you first get this denominator. This is called a Lagrange multiply. In the Calc 3, you learned a tiny bit. But my course in mathematics modeling and simulation take a whole chapter to talk about it. Because math, the most frequently used math tool is optimization, find the minimum and maximum. Not like the integration. Integration put another 2. From these 2 points, once you get this, you plug it in, and then you're going to find this regression line. That's basically, that's the line. And this line you can clearly see bisect these two closest points, right? Fair enough? That's not hard to understand.